Hi, welcome back. This is Vaseem, your teacher for analytical mechanics. In this lecture, I will solve one example from chapter 3, which is about oscillations. Chapter 3 has two parts. The first part of this chapter is about the free oscillations, harmonic oscillator without damping, and harmonic oscillator with damping. The second part of this chapter is about the forced harmonic motion. In simple words, in the first part of this chapter, we actually let the simple harmonic oscillator to do its own things without our interference. But in the second part, we impose our will onto the simple harmonic oscillator by deriving it with a force. In this lecture, I will solve one example which is related to the harmonic oscillator without damping. So for harmonic oscillator, the differential equation is mx double dot plus kx is equal to 0, or x double dot plus k over mx is equal to 0. So you have derived this in your theoretical class. I will just write the relations. So here the angular frequency is, in this case it is omega naught is equal to square root k over m, and the period of oscillation is t is equal to 2 pi over omega naught, or we can write like this: t is equal to 2 pi square root k over m. So this is the period of oscillation in case of harmonic oscillator. Sorry, it is m over k. T is equal to 2 pi m over k. Suppose we take the case of simple harmonic oscillator, and the period of oscillation is t is equal to 2 pi m over k. Here we take the ideal case, like the surface is frictionless and the spring is ideal. So this is the y direction, and here this is the spring, and at this position spring is relaxed. So if we extend the spring up to a certain distance, here the mass m is attached to the spring. So when we extended the spring up to this level, so this is the x position, so there is a restoring force. Maybe this color is prominent. So this force is actually the restoring force, and this downward, this is the mg because of the gravity, and this is n. So in y direction there is no acceleration, so we don't need to worry about the forces in the y direction. So here from the equation it is very simple that if you know the period and mass m, then we can calculate the k. Similarly, if we know the value of k and period, we can calculate the mass. So the point of discussion in this example is that this period, it is independent of this distance. So the period will remain same whether we extend this spring up to here with the same mass or up to here. So the period will be same. So here using the Newton's second law of motion, ma is equal to minus k of x. In other words, mx double dot plus kx is equal to 0, or x double dot plus k over mx is equal to 0. So now we need to find the solution of this equation. Here this x is changing in some way as a function of t. So what would be the solution of this equation? So I want to show you one animation, so I think after that you can write the solution of this equation. So in this animation the mass is 1, damping at this stage we want to put 0, it should be 0, and the spring stiffness is 10, spring length is 2.5, and fixed point is minus 2.50. So I will show you here, like this is the spring, and as its damping is 0, so if we drag it from 0 to 1 and then leave it, from here you see it will oscillate. So it is oscillating around 0. So this is the graph. Actually from here we just need the position, and you see this graph is sinusoidal graph. So from this graph, what do you think? What will be the solution of that differential equation? It should be cosine. As we have seen from the animation, we will substitute the cosine solution in this equation. Like the solution is x is equal to cos of omega t plus theta, and here it is constant a. This constant a is amplitude. This omega is angular frequency. And this theta is phase. So if we substitute t as 2 pi over omega in this equation, so the function will be like a cos of simply 2 pi plus theta. So what is the maximum and minimum value of 1? It is of cos 2 pi, it is plus 1 or minus 1. The frequency of oscillation is f is equal to 1 over t, which is in hertz, and here the angles are in radian. So if I advance this time by 2 pi over omega, then the angle will increase here by 2 pi radians. So the first derivative of equation 1 is x dot is equal to minus a minus a omega sine of omega t plus phi, and the second derivative will be like minus a omega square cos of omega t plus phi, and if we simplify it, so it is like minus omega square a minus omega square x, sorry. So we can put this equation into the first differential equation like this one. So here it is strange that this is independent of the amplitude A and independent of the phase angle phi. To start the oscillations, we have two choices, like from where we release the object and what is the velocity that we gave to the object. So let's solve an example. Suppose we have the initial conditions, like in this example we have initial conditions like x is equal to 0 or time is 0. The spring constant is 10 Newton per meter. The mass of the object is 0.4 kg. So what is x here? As a function of time, including amplitude and phase angle phi. So first we will solve the angular frequency. Omega is equal to, we know the equation, I will just put the values. It is 10 over 0.4, which is equal to 5 radians per second. And the period of oscillation, the period of oscillation is t is equal to 2 pi over 5, which should be around 1.26 seconds, and here the frequency is 0.79 hertz. So we know the equation is x is equal to a cos of omega t plus phi. So here we know that t is equal to 0 and x is equal to 0. So solution right here will be 0 is equal to a cos phi. Here we know that the a is not equal to 0. The reason is that we released the oscillator at equilibrium and gave the velocity of 3 meter, I think it is 5 meter velocity. I did not mention the velocity. So here the velocity is 5 meter per second. So we released the oscillator at equilibrium and gave the velocity of 5 meter per second. So amplitude A is not 0. So the only solution is that the cos phi is equal to 0. That means phi should be equal to pi over 2 or 3 pi over 2. So now the next condition is that v is equal to minus 5 meter per second, and the equation for velocity is x is equal to minus a omega sine of omega t plus phi. By putting the value of velocity and angular frequency, we can obtain the value of a. like minus 5 is equal to minus a 5, a t is equal to 0. So we have sine phi. If we pick the value of phi, which is pi by 2, then sine pi by 2 is equal to 1. So in this case, minus 5 is equal to minus a 5, a is equal to 1. So the solution which includes phi and a is x is equal to 1, the value of a cos 5t, the value of omega is 5, and pi by 2, which is the value of 5. So we see that the initial conditions determine the amplitude and phase angle. So this is the amplitude and this is the phase angle. So these two values are determined by the initial conditions. So I want to show you one example. So we have an object with mass 100 gram. So in this example, I want to show you that the period of oscillation is independent of the amplitude. So in first example, if we drag this object at position 1, so this is 1, and in the second case I will drag it up to here, up to 2. This means that its amplitude will be high, but in this case, so I have dragged this up to 1. So now I will start this animation and I will count up to 10 and we will check what is the time here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, it's back. Oh, it should be here, not here. So we will do it again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it is around 11.475. So we have to note it. This is 11.475. So this is case 1 when the amplitude was 1 centimeter. So here the period of oscillation is 11.475 seconds when the oscillation was when the amplitude was 1 centimeter. Now I will drag it up to 2 and then we will count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 11.5. 2 centimeter, amplitude is 2 centimeter and period of oscillation is 11.5 seconds. Actually this is the same, and this 11.5 is because of the human error. In the previous case it was 11.475 and now it is 11.525, and this small error is because of the human error. So we can say that the oscillation is same. Now we will check the effect of mass. So here the mass is 100 gram. We will keep the amplitude same and we will change the mass of the object, and we will check the effect of mass on the period of oscillation. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so it is around 11.475. Now let's change the mass of the object from 100 grams to 200 grams. One, 2, 3, 4, 5, 6, 7, 8, 9, 10. So here you see the period of oscillation is increased. It is 16.225 seconds.